Okay, so in this video we're going to look at SP15, the last chapter of Triple Science Physics. It's kind of divided into two sections really. You've got the materials, bending, stretching kind of thing, so springs and how they work. That's the first section. The second half is all about pressure and fluids. And floating and all that sort of thing. So we're going to take it in two halves. We're going to look at every single bit of the specification that you need to know, and we're going to focus on those bits so we'll be able to do it nice and quick and yet hit everything that is important for the exam board. So let's get started. If you need to pause the video to look at everything you need to know, then you can do, but we're going to look at each one of these things in turn. Each one of these is going to take at least one slide. So you won't necessarily need to do that, but if you do need to pause it and see it, this is all the stuff on springs. And this is one of two slides on pressure and fluids. And this is the second slide on pressure and fluids. So between those three slides you've just seen there, that's everything you need to know on this chapter in its entirety. So in the first part we're going to look at stretching things, really important physics principles at work here. All kinds of things are stretched in real life. Springs are a really nice, easy example of this, but when it comes to engineering and design and just the real world, there's all kinds of situations where things stretch and we want to know how far they stretch and why. So things like bungee cords and things like that, if you get that wrong, there are fairly serious consequences. So these laws and things that we're going to learn are important in a huge range of applications. So let's start with a nice straightforward one. It says explain using springs and other elastic objects that stretching, bending or compressing an object requires more than one force. Now if you apply one force to an object, you can get it to stop, you can get it to start moving, you can get it to change its direction. What you can't do with one single force is stretch, bend or compress something. So we'll look at springs a fair bit in this, but let's say for example we've got ourselves a Chinese bamboo flute. Let's have a look at those three things in turn and see how we need at least two forces for each of those things. So stretching, I am going to need to apply two forces, one going this way and one going this way to stretch. If I want to compress, to squeeze them together, I need to apply a force this way and this way to do it. So there's two forces there. If I just apply one, nothing's going to happen. When it comes to bending, you're going to need three forces, because if I just apply a force here and here, it's going to try and rotate it. So to try and bend it, you need at least three. You could have it, say, those three. So pushing down with this finger here, pushing up with this one, that would allow us to bend if the flute wasn't so rigid. But in general, yeah, anytime you want to compress, stretch or bend, you're going to need more than one force. Recall that, and there's your first one. Second point, describe the difference between elastic and inelastic distortion. Well, that's nice and easy. If I take my spring here and I apply a force to it and then I release it, it will go back to its original position, its original state. So that there that I've just done is known as elastic distortion, or sometimes known as elastic deformation. I've deformed it, but when I let it go back, it goes back to its original state. Now, sometimes children get their hands on these springs and they get a little bit overexcited. These two springs, as you can see, have been childified. So someone has pulled this too much, and as a result, it hasn't gone back to its original position. I can try pushing it back to its original position, but it doesn't like it. So if I was to continue to stretch it and pull it even further, then again it won't go back to its original state. That is known as inelastic distortion. So elastic goes back to its original shape and inelastic does not. So there was a guy who did a lot of work with this sort of stuff. His name was Hooke, and he actually came up with a relationship between the force that you're applying to a spring or something of a similar nature and the effect that you get, the extension of that spring. And the law that he discovered bears his name. It's known as Hooke's law, and it basically says F equals K times X. F is the force, so it's the amount of newtons that I'm applying to stretch my spring. X is the extension, and we'll see a little bit more about the extension in a minute, but it's the extra length that this spring is stretched. K is the, in maths you describe it as the constant of proportionality. He discovered that the force was proportional to the extension, so if you double the force, you double the extra length that it extended by. He discovered the two were directly proportional to each other. So if force is proportional to x, then force is some number times x, and that some number we call the spring constant. We'll look a bit more of that in detail in a minute, but yeah, the objective for this one just simply says recall and use this equation. So it's going to be one of those ones that you have to memorize. F equals K times X, Hooke's law. Hooke wouldn't have liked that, and Hooke and Newton had a very bad relationship, a lot of physicist beef. So what is extension? Extension, a lot of students get it wrong, so do be careful. This spring is 2 centimeters long. If I stretch it so it is now 5 centimeters long, the extension is 3 centimeters. It's the extra length. Sometimes people forget this and they talk about this is the extension, the overall length of the spring. No, it is the extra length that it's stretched, ignoring the initial length that we have there. Okay, so that's what the X stands for in Hooke's law. F equals Kx. X is the extension, the extra length of the spring after the force has been applied. So Hooke did these experiments, and as you can see, if we just bring our laser pointer here, let's see, lovely stuff. So what he did was he applied a load of forces to springs and he measured their extensions, and you got a graph like this. You can see if you double the force, then you're doubling the extension. And in general, we get this nice straight line through the origin. If it's a straight line through the origin, that means that the two are directly proportional. We have direct proportionality between the force and the extension. One of the nice ways of thinking about this, as we've used before, is that if you double the force, the extension will double as well. This was just kind of the pattern that he discovered. Now, if you use different springs, you'll get a different line with a different steepness or gradient, but you'll still get a straight line through the origin. And so this idea of how steep the line is gives us an idea of how hard we have to pull the spring to get it to stretch. So this one, for example, let's see, we've had to apply, say, 5 newtons of force to get it to stretch 4 centimeters. So you could work out the stiffness of the spring, usually known as the spring constant, K, by rearranging this equation. If F is Kx, if we divide both sides of the equation by x, we're going to end up with F over X equals K. So we've got this K is F over X here. In this case, it would be 5 newtons divided by 4 centimeters. This is what, 1.25 newtons per meter. So it tells you how many newtons you need to apply to the spring to get it to stretch every extra meter. So here's another example. If I have a spring constant of 20 newtons per meter, that means for every extra meter I want it to stretch, I need to apply an extra 20 newtons of force. So let's see how we can apply and use this equation, F equals Kx. So if I've got F is 30 newtons, so I'm applying 30 newtons of force to my spring, and I get an extra extension of 10 meters. Obviously not possible with this tiny spring. What is K? You can pause the video now to see if you can figure it out for yourself. 5, 4, 3, 2, 1. There we go. K is F over X, 30 over 10, 3 newtons per meter. You need to apply 3 newtons for every extra meter you want your spring to stretch. Here's another example. If I've applied 32 newtons to my spring, and my spring has a spring constant of 4 newtons per meter, what is the extension we're expecting to get? How far is it going to stretch? Is its extension? Again, pause and check to see if you can get it. 5, 4, 3, 2, 1. Here are your answers. X is F over K. All we've done with the equation there is we divided both sides by K to get X is F over K. 32 over 4, 8 meters. Our spring will stretch 8 meters of extension. So here are two springs, spring X and spring Y. You can see here that spring X requires a larger force to get the same extension as spring Y. So here, for example, if I apply 50 newtons to spring X, it will stretch by 0.5 meters, but I only need to apply 20 newtons to spring Y to get it to stretch the same amount. So I would describe spring X as stiffer than spring Y. I would say it has a larger spring constant. But it turns out if you work out the gradient of the graph, it tells you exactly what the spring constant is. Think about it this way: if I'm looking at X, spring X here, this line here, to work out the gradient, it's going to be rise over run. So the rise of this is 50 newtons, that height there, and the run of it is 0.5 meters. That's the extension. So if you were to work out the gradient of this graph, it would be your force divided by your extension, which is basically what your spring constant is anyway, right? So your gradient of this graph will be the spring constant. So this one, it would be 50 divided by 0.5. For spring Y, it would be 20 divided by 0.5. Both of those will be the spring constants for those two materials, and the spring constant for Y will be less than that for X. 15.4. Now, if I take my spring and stretch it, I'm having to apply more and more force to stretch it further and further. That's true. But I also need to put in more energy to do it. It's storing more energy. The more I pull, the more energy is being stored. And of course, I can release it to get the energy back. It will ping back to where it was before. But how much energy is stored? Well, there's this equation to work it out, and in A level we show you where it comes from. It's very straightforward, really. But we don't have time for it today, so we're just going to take it as fact. I promise you that it comes from a logical place. The equation for the energy stored in a spring is half times k times x squared, and k and x mean the same as they did in the last equation. So nice and straightforward. Half times the spring constant times the square of the extension will tell you how many joules of energy is stored inside that spring as you stretch it. Or alternatively, you can think of that as how much energy you need to put in to stretch it. Same sort of thing. So here's an example. How much energy do we need to put in to stretch a spring if the spring constant is 4 newtons per meter rather, and the extension is 3 meters? Give you a moment to work that out. 5, 4, 3, 2, 1. Here's the answer. The energy is half times k times x squared, so it's going to be half times 4 times the square of 3, which will give you 18 joules. It takes 18 joules to stretch that spring, and it stores 18 joules of energy as a result. How far will the 10 newton per meter spring stretch if 80 joules of energy is used? You'll need to rearrange the equation for that one. You can pause the video. 5, 4, 3, 2, 1. There we go. Energy is a half times k times x squared. If you want to figure out how far it's going to stretch, you're trying to work out what x is, aren't you? So if we try and get rid of all the stuff in front of the x, there's a half there, so let's just double both sides. We'll end up with 2e is equal to kx squared. If you divide both sides by k, you'll end up with 2e over k gives you x squared. There it is. Now, if you know what x squared is, that makes things nice and easy. All you need to do is square root that to get what x is. So x squared will give us 160 over 10, because we've got 160 is twice the energy. 10 is the spring constant here. So that's what x squared is. X squared is 16. Now, of course, we can square root that to get what x is, which is 4 meters for that one. Maths fans, of course, you'll know that the square root of any number will be either positive or negative. So this could be -4 mathematically. Of course, -4 meters of extension makes no sense at all. So we'll just leave things nice and positive. 15.5, the difference between linear and non-linear relationships. You need to be able to describe these. So first of all, this graph looks a little bit strange because it's not going through the origin, but you'll notice that we're not actually plotting extension here, we're plotting length, and this length here is the length of the unstretched spring. So essentially, if we were going to plot extension rather than length, this line would go through the origin. So it is directly proportional. up to a point, because if you continue to stretch the spring, weird things start happening and it stops obeying Hooke's law. We get this kind of curving pattern here, a non-linear relationship. Non-linear meaning it's not a straight line anymore. So spring will obey Ohm's law up, not Ohm's law, it will obey Hooke's law up to a point. If you stretch it too far, the line starts curving and it's not obeying Hooke's law anymore. It's not a linear relationship anymore. Now, this is also true if you start looking at other materials. So an elastic band, for example, we'll do, we'll give you a different type of graph. You can see here, we start off with a very steep part, which means that we're having to apply and to increase our force a lot to get a little bit of extension. And you'll know this if you've got an elastic band. If you start pulling it a little bit, it doesn't give all that much. If you continue to stretch it, then you still need to continue to increase the force to get more extension, but the payoff is bigger. You get a bigger extension through increasing your force after a while. But then you get towards the end of this, when it starts curving upwards again, where you get kind of like the end, the limit, if you like, of the elastic band, where now you're having to put in a large force to get any extra extension. So all of that is a non-linear relationship. It's not directly proportional at all. It's not a straight line on the graph. Then the final part of the objectives for this is just the core practical, which of course you will do in class. We can't really do that one through YouTube. So just to give you an idea, this is what you'll do, stroke have done, depending on when you watch this. Task and method, you can check that. Anything that you're not sure of course, you can ask in class. So here are your objectives. You can pause the video and look through them, and if there's anything that you're not sure of, you can go back to the relevant section. But there you are, that's 2 sections done in, according to my clock, just under 17 minutes. So we're now going to move on to have a look at the second half of the section. We're going to look at pressure in fluids next. So here's our pressure section. We're going to think about, first of all, pressure as a whole, how to work out pressure of any sort of material, sort of solid or liquid or whatever. And then we're going to focus later on how pressure in liquids and gases works. We'll call liquids and gases fluids as a general term, anything that can flow. So gas is a fluid because it can flow, liquid is a fluid because it can flow, a solid is not a fluid. So when it comes to pressure, this stuff is pretty straightforward. This has been sort of a staple of the Key Stage 3 syllabus for a while now, but with the rejigs you may not have covered this particular bit. But it's very straightforward. So if I apply a certain force to a certain area, I can calculate the pressure by dividing the force I'm applying by the area. The equation we'll see in a moment is pressure is force divided by area. The first thing you need to be able to do is apply this to different situations. So it's all about how we're spreading our force over a particular area. If you concentrate your force into a tiny area, you've got a lot of pressure there. If you spread your force out, you've got hardly any pressure. And this has a huge range of different applications in real life. The person on the left is a clever pin user, a person who can adequately use a push pin. Notice how they've got it the right way round. The pointy end is in towards the pin board, and the flat wide end is where her or his finger is. That was a tortuous sentence. So here's the idea. When you apply a force to your pin and you push it in towards the pin board, because of Newton's laws and every action having an equal opposite reaction, etc., whatever force you're pushing into the pin pushes back at you with the same force. But the clever thing about a pin, if you can call it that, is that it's got a wide area, which means that the force that it's applying to you is spread out over that wide area, and so the pressure is actually quite low on your thumb. Whereas the pointy end that's in towards the pin board, all that force is concentrated in a tiny, tiny area, and so because it's so concentrated, you've got a really large pressure that will allow it to go through into the pin board. The person on the right hand side is an inadequate pin user, a pin user of considerable stupidity. this person hasn't really worked out the right way to use the pin. They've got it backwards. This point, of course, again, the forces are equal, but because they've got their thumb on the pointy end, where the area is much smaller, all that force is concentrated into a tiny spot on their thumb, and it is likely that sad times will result in the very near future. It's not going to go through into the surface below because of all the pressure at the bottom, right there, is spread out over a much larger area. That's one very obvious example of pressure, but there's lots of others, and you need to be able to identify them. So let's have a look at a couple more. Here are a couple. If you've got two people who have the same weight, but one of them is wearing stilettos and one of them is wearing slippers, the person with stilettos will have much greater pressure because the force of their weight is acting on a much smaller area. So if the two of these people start walking through a muddy field or over snow, then stiletto person is going to sink down because their pressure is greater. If you really want to make sure you don't sink, use snowshoes. This snowshoe here has a massive area, so we're spreading our weight over a much larger area than before. Pressure is greatly reduced and you are not likely to sink down as much. Finally, here's another one. If we use a dull knife, the knife blade is not sharp by definition. The area of it is much larger, so we're applying that force over a larger area. The force isn't as concentrated, there's less pressure, it's not going to sink into the material very well. Nice sharp knife, it's got a very small area that we're applying that force to, and so the pressure is going to be really large, and that's going to mean that it will slice through the tomato with no difficulty at all. So just a couple of real world examples. There's all kinds of situations where pressure is important. Sometimes you want a lot of it if you want to cut or pierce. Sometimes you want very little of it if you want to sort of not cut or pierce, sort of stay upwards in the snow, for example. Good. Now here's the equation. We've kind of touched on it already, but pressure is force divided by area. It says recall and use it, so you're going to need to memorize it. Pressure is force over area, which is kind of the definition of what it is, and you'll notice it's measured in pascals. 1 pascal is the same as 1 Newton per square meter. There's an extremely funny physics joke about that. Sadly, we don't have time to go into it today. But yeah, pressure over area gives you the force. We need a couple of examples of this to see how the equation is used. So here it is. We're going to look at the pressure from a woman in stilettos and an elephant. So these are all sensible numbers for it. I haven't just made them up off the top of my head. I've done a bit of internet research, as you do. Woman in stilettos, weight is roughly the weight of a person, so about 650 newtons of force pulling down on her body, and the area of the stilettos is 0.0002 square meters. That translates as 2 square centimeters, because there are 10,000 square centimeters in a square meter. I'll ask if you're not sure why that is. So the first part of the question, you need to calculate the pressure from the woman using the equation, and the second part of the question, you're given the pressure from the elephant. You need to work out the area of its feet. 5 seconds to work that out. You can pause the video. 5, 4, 3, 2, 1. Those were definitely not seconds. Right, here you go. First one, pressure is force over area, so 650 newtons over 0.0002. That's interesting. There appears to be more noughts in my answer there than there is there. That's unfortunate. Let's pretend that didn't happen. Turns out the answer is 32,500,000 pascals if you do it right and don't type it in very poorly like I've done there. Second one, pressure is force over area, so area is going to be force over pressure. You can do that from the formula triangle or just by regular rearranging. So force over pressure is going to be 40,000 newtons of weight divided by 250,000 pascals. That's going to give you an area of 0.16 square meters. That's the total area of the 4 feet of the elephant on the ground there. So you'll notice the pressure from the woman is far greater than the pressure from the elephant, even though the elephant has got a significantly larger mass. That's because the pressure from the woman is focused on a much smaller area with the stiletto heel. So the stiletto heel going into your foot in some ways it's going to hurt more. This, incidentally, is assuming that the woman has kind of rocked back on her heels and she's not putting any pressure in from her toes. It's just on the heels there. So yeah, that is how you work out your pressures. 15.9, so we now get into the ideas of pressure of fluids. So fluids, remember, include liquids and they include gases. And this bit that says, recall that the pressure in fluids causes a force normal to any surface. So if you remember that, you're sorted with this. So the idea of normal, as you may remember from optics, when we looked at the idea of refraction. In fact, we've got a board here. If I was to draw a perspex block and show you a ray of light going into the block, if I was looking at the angles, there we are, I would need to measure those angles from this line here, the normal. The normal is at 90 degrees to the surface. And when we talk about a force normal to a surface, we're talking about a force at 90 degrees to the surface. So if I've got a surface here, which clearly I do, then 90 degrees is like that, where the pen's pointing. So if we're talking about a force normal to the surface, it's a force going right into the surface like that, normal to it, perpendicular to it. So it turns out that the pressure from fluids is always 90 degrees to the surface. You can see it from the pictures down there. The force is always at 90 degrees. Even if the particle is hitting an angle, the only way it can transfer a force is at 90 degrees, because any force this way is not going to have any effect on the surface. So the force is always, and the pressure is always at 90 degrees to the surface of the material. You can see in the picture there as well a couple of extra rules about pressure. Describe how pressure in fluids increases with depth and density. So this is a fairly straightforward one. The deeper you go, the more pressure you've got. And the more density you've got, the more pressure you've got as well. Why is that? Let's have a look at this tank. This tank has got 3 holes in it. You can see the water is coming quite slowly out of the top hole, coming very quickly out of the bottom hole. The reason for that is quite simple, really. The water at the top has only got this amount of water above it, and that's what's weighing it down and causing that pressure. The spout at the bottom, all the water here is under much, much greater pressure because there's this whole weight of fluid above it there, which is really pushing down on it and squashing it. So pressure increases the deeper you go. If you've got more dense liquid as well, or more dense fluid in general, you're also going to increase your pressure. So a larger density will result in a larger pressure. So it turns out we can actually work out the pressure caused by being in a depth of fluid, and the equation is here, is P is H times rho times G. This is not P. If you think of it as P, it's going to get really confusing because this is a letter P. This is your Greek letter rho, which is the symbol for density. You'll remember that from chapter 14 when you did some density calculations. So the pressure that you've got is going to be equal to the height of the column of liquid above you. So you can think of it as how deep I've gone into my liquid, multiplied by the density of the liquid and multiplied by the strength of gravity, which on Earth, of course, is 10 newtons per kilogram. So let's take an example. P is H times rho times G. Let's have a look at the question. What's the pressure 20 meters under the ocean? We're going to ignore the fact, by the way, that there is some pressure that comes from the air above that, the water in the first place. We're just talking about what's the pressure from the ocean itself. So we've got seawater with a density of 1030 kilograms per cubic meter. We've got the pressure of a depth of 20 meters. So all of those things in the right units. We don't need to convert anything. See if you can work it out. I'll give you 5, 4, 3, 2, 1. Here are your answers. P is H times rho times G, which is 20 is height. Density is 1030. G is 10. Times them all together, that will give you 2.06 times 10 to the 5 pascals, or 2.06 times 10 to the 5 newtons per square metre, means the same thing. You could write that as 206 kilopascals if that's the sort of thing that brings you joy. Second example, let's have one where we need to do a bit of rearranging. So we have a 30-metre column of liquid. So we're looking at the bottom of this 30-metre column of liquid. At that point, it's got 6 pascals of pressure. What's the density? You'll need to do some rearranging on this one. You can pause the video. 5, 4, 3, 2, 1. Here it is. P is h times rho times g. Careful as we rearrange this. We want to find out what this rho thing is. So we need to divide the right-hand side by h and g. So we need to divide the left-hand side by h and g. So we'll end up with rho is p over h times g. You must make sure it's in the brackets when you type it into the calculator. If you do it properly, it'll be 6 over 30 times 10. Which give you 0.02 kilograms per cubic metre. If you forget the brackets and you just do 6 divided by 30 times 10 in the calculator, it will do 6 divided by 30 times the whole thing by 10. You'll end up with an answer of 2 rather than 0.02, which is the wrong answer and not the one you want. Okay, so 15.13. We're now getting to sort of trying to describe what's going on with these fluids. Why does it increase? And why does it vary? We've already said that it increases, so as you go deeper down, you get more pressure. We've basically answered this already. As you go deeper down, you've got a larger weight of fluid above you, so it's going to be squashing you more. In terms of the density, if you're in a really dense liquid and you go deeper down, or if you go to the same depth, but you just change the density so it's a more highly dense liquid, then you're going to have a heavier mass of fluid above you. So if I went 20 meters down in water, that would give me a decent amount of pressure. If I went 20 meters down in a tank of mercury, which is liquid metal, very, very heavy for its size, very dense, I would find a much greater pressure squashing me than I would for water at the same depth, because it's heavier for its size, it's more dense. And you can apply the same sort of thing for atmospheric pressure. So we're in a fluid, it's like being in the bottom of a tank of air when you're on the surface of the earth. If you go higher up, then there's less air above you. And it turns out that the air is more dense down here than it is up there as well, because most of the air is pulled down by gravity. So if you go up to the top of a mountain, the air becomes thinner. There's less of it, it's less dense. So if you go higher up, the density of the air decreases, and you've got less air above you, so the pressure will decrease. And that basically answers that one, really, is the idea of the Earth's atmosphere being denser at the bottom than at the top. And if you continue going up, of course, you kind of run out of air. So from Northampton to London, very roughly, about 100 kilometres that way, horizontally. If you go vertically 100 kilometres up, you reach the edge of space and you lose the atmosphere. There are no air particles there at all. So hopefully that's something you're aware of. You know, as you go up, you start to lose air, and eventually you get to the point where you run out of atmosphere. There's no air there at all. And so if you go really, really high up, you need to have your own air supply. So planes will have pressurized cabins where they'll artificially put in loads of air, because if they had the windows open, then you wouldn't be able to breathe, and that would be bad. Getting towards the end now. 15.8. Describe pressure in a fluid as being due to the fluid and atmospheric pressure. We've kind of talked about this already, but let's make sure we've consolidated it specifically for this point. Here is a little killer whale or orca, and we're looking at this little square area on his or her back. The pressure on here is due to two factors. It's due to all of the water above it, which is in this kind of squarish column here, this cuboid, but also the air above him. It turns out the weight of the air above you is actually quite considerable. If you were to look at the column of air straight above you, straight from your shoulders and head and you straight upwards, the weight of the air all the way up to the top of the atmosphere on you is about the weight of a small car, believe it or not. So the pressure on you is about 100,000 pascals just from the air. So we can't discount this fact. we've got all this air above us, we do need to take it into account. But when you start diving to deeper and deeper depths of the ocean, the pressure becomes much more to do with the water. And the reason for that is the water is much more dense than air. So you don't have to go too far down into the water before the air pressure isn't all that significant compared to the weight of all the water above you and the pressure that gives you. So here's a couple of things just to kind of summarize some of those ideas. We've got this person here, the pressure is acting normally on them. It's going in 90 degrees to the surface of their body. And we can see that it's basically the same size in all directions pretty much. We've got this person down here. They've got much more pressure on them because they've got the weight of the water above them as well as all the air. And if we look at the pressure on the bottom, well, on the surface of the seabed there, it's due to all of the weight of the water above it and all of the weight of the air above it as well. Okay, so this is where it gets a bit interesting because we're looking here at how we're actually able to explain why we have upthrust as a force in the first place. You may not have thought about this before, but we know that when we get into a tank of water like a swimming pool, we feel lighter. We feel there's this force pushing us up, this buoyant force or upthrust. But where does it come from? Well, you now know all that you need to do, or you now know all that you need to in order to explain where that force comes from. Take this shark, for example. It will come as no surprise to you, I hope, that the top of a shark is higher up than the bottom of a shark. So if you look at the top of the shark, it's got a certain pressure on it. The bottom of the shark is deeper down because it's the bottom of the shark. Now that actually makes a bit of a difference because we know that pressure is larger the deeper you go down. So this means that the pressure at the bottom of the shark down here is actually larger than the pressure on the top. And so those forces aren't actually going to cancel each other out. There's an overall upward force because the pressure on the bottom of the shark, which has to be pushing upwards, is larger than the pressure on the top of the shark pushing downwards. So there's this overall upwards force, and we call that upthrust. So if you put an object in fluid, it gets this upthrust force because we've got this force pushing up because of this imbalance of pressure. You've got more pressure from when it is low down compared to the pressure on the top there. If it's fully immersed in your fluid, then that's the case. If it's partially immersed, that's even more the case, because if you've got something that's, say, floating in some water here, the pressure at the bottom is coming from the water. The pressure at the top of the object is outside of the water, so it's just coming from the air. So there's a big difference there in terms of the difference in pressure. So our final thing to do really is to understand where this upthrust force comes from. We've described it in terms of pressure. There's one more way you can think of it, and that's to do with the weight of the fluid displaced. So let's have a look at this picture. In the first picture, we have a rock on the end of a string, and it's in some fluid, and we've got a reading just about there on the Newton meter. When we pull it out of the liquid, the reading on the Newton meter goes up. So that tells me that when it's in the fluid, we have to pull up on it with a smaller force, and the reason for that, of course, is that this situation here, when it's in the fluid, it's got some upthrust, which kind of counteracts the need to be pulling it up with the Newton meter. When you take it out of the water, no upthrust, so it's going to weigh. It's going to feel like it weighs more. Of course, technically, its weight hasn't changed. What's changed is that we don't have the upthrust anymore, so the Newton meter reading is going to change. Now, how much upthrust we get, we can think of it in terms of the pressure, but there's another way of thinking about it as well. Let's have a look at picture 2 here. If I take one of those displacement cans that you used earlier on in chapter 14 to work out the density of something, if I take my stone and I put it into the water, what it will do, of course, is it will push out its own volume in water. So if the stone takes up 50 cubic centimeters of space, it will push out 50 cubic centimeters or 50 milliliters, same thing, of water out into in this case this beaker that's going to collect it here. Now it turns out, as you can see from the statement at the top, if you weigh this fluid here, if you weigh this liquid, this water, the weight of the water will be exactly the same force, same size force, as the upthrust pushing up on this rock. So we can work out what the upthrust is if we have a look at these two readings here to begin with. We look at this one here and this one here. The difference between those two is going to be the upthrust, the force upwards. If you weigh the water, it will have the same weight as that upthrust that you might have worked out in the first part. So we say that the upthrust is equal to the weight of fluid displaced. If you push away 3 newtons weight of water away, then you've got 3 newtons of upthrust pushing you up. To finish off that idea, let's have a look at this this diagram here. This will kind of put a cap on this. We've got 4 different types of wood of varying densities. Let's start with the balsa. The balsa wood is very, very light for its size. It's got a very low density. In this case, 160 kilograms per cubic meter. Now, when you compare that to water, which is 1,000 kilograms per cubic meter, you can see it's got a very low density. So, this cube here would have a weight, say, of 1.6 newtons pulling it down. You'll notice it's sunk just a little bit into the water, and it doesn't have to go very far before it's pushed away 1.6 newtons of weight of water away from it. And when it's doing that, it's got 1.6 newtons of upthrust, which will cancel out its weight and stop it sinking any further. So the balsa just sits almost entirely at the top and just sinks just a little bit under the water surface, and it's just pushed away 1.6 newtons weight of water away from it, enough to cancel out its own weight. Let's take the oak. The oak's got a much larger density, 750 kilograms per cubic meter, so the same size cube will weigh a lot more. This one weighs 7.5 newtons. You can see it still floats. It's pushed away, not now 1.6, but it's pushed away 7.5 newtons worth of water away from itself. So it's had to sink down further to do that, because 7.5 newtons weight of water will have a larger volume than 1.6 newtons, of course. Same thing with the teak. The teak's got a larger density still, 900 kilograms per cubic meter. It's got a weight of 9 newtons in this case, so it's got to push away 9 newtons worth of water. So if you were to take this volume of water that's pushed away and weigh it, it would weigh 9 newtons. The ebony is an interesting one. It's got a density greater than water, and you can see it's got a weight of 12 newtons. It can't push away enough weight of water for it to float, the ebony, because it weighs 12 newtons, but if it pushes away its entire volume of water, it's only going to push away about 10 newtons worth of water, which means that we've got 10 newtons worth of upthrust, but we've got 12 newtons worth of weight, so there's an overall resultant force of 2 newtons downwards. The thing's going to sink. So ebony will not float. It's a wood that will sink. It's very, very dense. Balsa wood, very, very small weight, floats very, very well. Doesn't sink into the water much at all before it's displaced its entire weight in water, and that's the point where it stops. So if you followed all of that, you should be able to hit that objective. Explain how the factors of upthrust, weight, density of fluid influence whether an object will float or sink. You'll notice the water has a density of 1,000 kilograms per cubic meter. If the object's got greater than that density, it will sink. Now we could repeat the experiment if we wanted to with a really dense liquid like mercury, for example, and you'd find that even ebony was able to float. That's because mercury is very dense, very large weight for its size, very large mass for its size. One affects the other. So the idea behind all of that is that if you've got a very dense liquid, then you'll be pushing away a much greater weight of it as it goes down, and so you can get things to float. So for example, a cannonball will sink in water, of course, but it will actually float on mercury. You can watch videos of that on YouTube of people dropping cannonballs into big tanks of mercury. Now, unfortunately, this won't actually play for us. You can see the video itself. If you start it at 2:07, I'll put a link to the video here in the description if you want to watch this. Just very briefly, it's a big aluminium tank, or some sort of metal, I guess. You can see a GoPro video or some sort of video on the inside of the tank, and what they've done is they've heated up the air and they've vented it so that the air can sort of get in and out. They've closed the chamber entirely, so it's completely sealed off, and they've let the air particles cool down. And when they do that, they're not moving as fast, and that will change the pressure inside. Imagine I've got my Coke can here, or Pepsi. Other drinks are available, and let's say that I seal this after heating up all the air inside it and then let it cool down, which is basically what the video will show you. The particles inside are continually hitting into the surface of the can and exerting a pressure, and the inside pushing it outwards. At the same time, all the air in the room is squashing it inwards. At the moment, those two forces are equal, but if I was to heat up the air and then seal the thing and then let it cool down, when those particles slow down, they don't exert as much force pushing it outwards, but we've still got all that force pushing it inwards. Now, you might be able to have a bit of a think about what would happen if we did that to the extreme. If you watch the video, you'll see it happening on a much grander scale than we have there with the can. But as I say, the link to that will be in the description. Okay, so that is it. We're going to have a couple of slides now to remind you of the things that you should have learned. So if you want to pause the video, having a look, if there's anything you're not sure of, you can go back to that original section. You might have noticed the fluid section wasn't in numerical order. That's because the specification has it in a weird order that doesn't make any sense. So yeah, sorry about that. So here's slide 1 of 2. You can pause and check to make sure you've understood it all. And here's slide 2 of 2. If you've got that, then you've got everything that you need to know for this section of chapter 15. Okay, just to finish off, to make sure that you are confident with this stuff, there's going to be a couple of slides with exam questions on. And again, you can pause it, have a go at the question, and then the mark scheme will follow, so you can check to see how you've done. So here's our first question. You pause it and have a go. Mark scheme coming up on the next slide. 5, 4, 3, 2, 1. There it is. And our next question will be a 6 marker. There it is. Pause it and have a go. Mark scheme is in 2 parts, as it always is with the 6 marker. So in a minute, when you see the slides, the first slide will tell you the sort of stuff that you could say. You don't have to hit every point, but the sort of stuff that you could say to answer the question. The second slide will be a general description of how your answer should be. So let's have a look. So here are your points of what they call indicative content, the sort of things that you could say in your answer. And here are your points, your general idea describing what your answer should be like. Of course, we're aiming for the 5 to 6s. The more marks, the better. Just in case you needed to know what the maths content was, if there's anything looking on that list that you're not sure of, again, ask your teacher. And that is it, ladies and gentlemen. That is the last chapter of physics done. We will, of course, have time in class to have a go at some questions on this to make sure that you've understood it. But hopefully, in that roughly 50-minute video, you've seen the entire chapter done from start to end, and hopefully it's made some sort of sense. Do ask if there's anything you're unsure of. And that's it. Congratulations, you're done.